Okay, in this lab, we're going to be looking at how we can identify different substances by the light they emit when we give them energy, when we excite their electrons, and the electrons go back to kind of their stable place and release that energy. We can kind of compare it from one element to another. Specifically, we're going to be looking at metals because they tend to hold their electrons a little more loosely. So if we want our electrons to be kind of jumping out farther into the electron cloud and then coming back to release light, it's going to be a little bit easier if we've got something that is a little less kind of needy with its electrons, a little less greedy. It'll let them move a little bit. And we're also going to use ions in this case just to kind of make it a little bit easier again for kind of dissolving the metals. We're not taking just a solid chunk of metal. We're going to be using solutions where the metals are dissolved as ions in there. Okay, so specifically, metals tend to form cations. They end up losing electrons. So either losing 1 or 2 or 3 or so electrons. The metals we're going to be using are going to be short a couple electrons. So their electron configurations should match a noble gas, like something in column 18 or group 18. And, you know, if you can't remember which one's which, cation or anion, remember cations are positive. Ha ha ha, very funny. Anyway. So we kind of know the electron cloud to be pretty complicated, with s orbitals being spherical, p orbitals being kind of like these hamburger bun looking things, d orbitals getting all kinds of weird with these four-leaf clover sort of shapes, and this thing with a ring around it, and f orbitals are just wild. So these are kind of depictions of what the orbitals of an atom might look like more accurately, as they kind of stack up on each other, you know, as we get further and further out into the valence electrons and stuff like that, especially for really big atoms, like where you see like all these s orbitals stacking on each other here. However, trying to keep track of how electrons move through the electron cloud, and I say move in kind of air quotes, because it's a little more complicated than that, but it'll work for now. The way electrons jump or move through an electron cloud is really hard to think about if you're trying to imagine these complicated shapes. So we typically fall back to an earlier model of the atom to do this. That's not the most accurate model, but it is a lot easier to process. So we're going to look at the Bohr model, okay, where we have energy levels. So anything like in the second energy level, like a 2s or a 2p, we don't care. We just put all together into the second energy level, and all the electrons are there. All the stuff in the third energy level, 3s, 3p, 3d, just winds up in the third energy level, the third ring, and so on and so on. Okay, so what we're going to be doing is taking these metals, and we're going to put some energy in, either as heat or electricity or light or something, in order to energize their electrons. Now, where the electrons usually sit, whether we kind of write them out in the electron configuration, is called the ground state. These are where we expect to find the electrons, you know, and what orbitals they're kind of occupying. But if we go and shake them up with some energy, again, heat, light, electricity, something, they can get a little more daring and move a little farther out than they're usually meant to be. So rather than our valence electrons sitting at their normal spot, kind of in their lowest energy orbitals possible, maybe they stray out a little bit farther and they reach an orbital that's a little higher in energy, a little farther out from the nucleus. Okay, so we might say this as the electron jumping out to a higher energy level, okay, out farther from the nucleus. Okay, whether we look at it as an orbital or an energy level like this, this is called excitation. We are exciting the electron. We're getting it moving more, and it's going to move out farther than it usually would be. So it's going to be less comfortable, but as long as it's got that energy, it's going to be okay with that. Okay, now it can't do this forever. So at some point, it's got to return back home from the excited state that it's currently in back to the ground state where it kind of belongs. Okay. Now, since we took energy in to get the electron to quote unquote jump out to a higher energy place in the electron cloud, if it returns, it's got to use that energy for something. It's got to expend it. So we end up releasing that energy back out, as light. So whether we are taking in that energy as heat or electricity or light, okay, typically we're going to see light being the mode of that release of energy. We're going to emit light. Okay, we call that process de-excitation. Okay, so as the electron de-excites back from the excited state to the ground state, we lose that energy as light. Now, how does this help us? Well, the color of light that we release has to do with how far this electron jumps, okay? How much higher in energy did it get compared to where it started from? Okay, so depending on what element we're using, what metal we're throwing into the fire, in this case, we're going to see different colors of light come out as they have different electron configurations, and so our electrons are going to move out from the nucleus in different ways. Okay, so between our 7 metals or so that we're going to be checking here, we might get some colors kind of like this. All right, and we're going to have to try and sort of identify an unknown based on some known chemicals that we do use. So you'll have your set of 7, you test it in your flame, get a color and say, okay, so sodium gave off this color of light, or calcium gave off this color of light, potassium gave off this color of light, and then use that to identify a chemical we don't know off the top of our heads, see which one it matches. Okay? The color of light that we get out, again, tells us something about how the electrons move, and we aren't going to worry about, where exactly the electron goes from this energy level to that energy level, because that's very complicated and it doesn't really help us much. Okay, but you can kind of think about it, just kind of for funsies. Our color of light gets more energetic, gets higher in energy as we go further down through the rainbow. So red light is pretty low energy for visible light, and violet light is very high energy for visible light. Then you have kind of the progression in between. So we go from red to orange to yellow to green to blue to purple in order of increasing energy of light. So if we have something releasing violet light, that's quite a jump for the electron. That's quite a journey. If we have something releasing red light or orange light, not so much, kind of a small trip. To do this in the lab, we're going to turn on a Bunsen burner. Remember that your gas valve handle points out towards the nozzle, towards the hose, to get the gas flowing. You're going to have a striker that has a piece of flint on there to make some sparks to light the gas. If it takes you a little bit too long to get the gas going, just turn the handle, turn the gas off, let it air out for a second so you don't hit yourself with a fireball and spook yourself. All right, and then keep trying until you get it. Remember, it's not about how fast you move the flint on the striker. It's about getting it to really scrape hard. So focus less on getting it to, click a whole bunch of times, and more on really getting it to grind and scrape against there to get some good sparks. We'll only need about 3 or so drops of these dissolved metal ion solutions on the end of a Q-tip to get these tested, and we're just going to run them up and down through the edge of the flame to see the color of light that's released from that metal's electrons. Now, if we tried to stick the Q-tip directly into the flame, it wouldn't do much good, because we'd see a whole lot of light coming from the burning of the Q-tip and not from the electrons getting excited from metal. So we, again, want to just go up and down the edge. If your Q-tip is burning, you've got either not enough liquid on there, not enough of that dissolved metal, or you have put your Q-tip too far in. Might take a little bit of time for the color to show up, but it will show up. Okay, so as the electrons de-excite from their excited state, they will release light, and we can kind of make note of what color that is. And when you're done, we'll just close the gas valve. And of course, always be aware of where your fire safety stuff is. Keep your hair up and out of the way and things like that. So what's this going to look like for us? So as you go through each metallic ion, like sodium, potassium, lithium, calcium, strontium, barium, and copper, and one of the unknowns that's going to match one of these 7 here, you're going to note the flame color. Okay, put it in your best words, put it in your best explanation. So maybe don't just put red, maybe flavor it up a little bit. Maybe it's like scarlet or a deep red or something. Get creative with it if you can. Some of them will have similar colors, so they aren't all going to be individual colors. So, if two of them show up red, try and make them, different from each other. Try and explain how it's not exactly the same color of red, and that's helpful. We can look at how many valence electrons each one of these is going to lose. Now, typically, we would write out the electron configuration. We would look at whether it's easier for the element to gain or lose electrons, to become stable, to be like one of those column 18 elements. Typically, that follows the octet rule. What's the quickest, easiest way to get 8 valence electrons? Either by gaining electrons up to 8 or losing your valence electrons to get the previous set of 8 kind of closer in the electron cloud. In this case, we can kind of take a shortcut. Since we already know how positive these ions are going to be, like sodium has a positive 1 charge here, that means it lost 1 negatively charged electron. So how positive it is can tell you how many electrons that you have lost in the process. So for instance, our calcium has a positive 2 charge, so that means it had to have lost 2 electrons to get a charge of positive 2. All right. The ion's electron configuration is just like the electron configuration of the element, but we've lost an electron or 2 to become an ion. So, for instance, sodium's electron configuration would usually be 1s2, 2s2, 2p6, 3s1, but we lose that 3s1 electron to become an ion, so all that's left is this 1s2, 2s2, 2p6. This should match one of the elements in column 18, one of those noble gases, okay? And a lot of times, it will hit the octet rule by having 8 valence electrons in that new outermost energy level. Some of them are going to get a little weird, so they won't all kind of fit that nice, perfect octet rule. Copper is an example of how this gets a little odd, but other than that, they're pretty straightforward. And I did copper for you because, again, it's a weird one. Okay, so use this to help you out. Look at the charge, figure out how many valence electrons are lost, and I would write out what your typical electron configuration is for the element. It's like calcium, let's see, I think it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and I think we stop there. Well, if it lost 2 valence electrons, all right, and our farthest out energy level is the 4s, those are going away. And what we're left with is this right here, 1s2, 2s2, 2p6, 3s2, 3p6, which I think is argon's electron configuration, but I'm not entirely sure. I have to go back and check. So don't quote me on that. Okay? So check out what your flame colors are going to be. Figure out your valence electrons lost. Write out your electron configuration. And then there are a couple extra questions on the lab that have to do with excited state, ground state, what kind of errors could come up in this lab, ranking the energy of the light from the flame color that you see for each element. Remember, red light is low energy in terms of visible light. And as we go through the rainbow, down to violet, we get to higher and higher energy light. And that corresponds to a bigger jump for our valence electrons, moving out farther and farther into the electron cloud, kind of jumping out farther.
So this Bunsen burner is going to be our energy source for getting our electrons excited. When the electrons in that valence energy level, those farthest out electrons, get excited when they absorb energy, they're going to be able to move out farther in the electron cloud to a higher energy orbital. Since that's kind of an uncomfortable position, they can do it as long as they can hold on to that energy, but at some point they got to go back to their comfortable place, which we call the ground state. When they return to the ground state, they have to do something with that excess energy, so they release it as light. So what we're going to do is basically put energy into some different chemicals. We're going to use metals because they hold on their electrons a little more loosely, so we can get some better jumps out of them. And we're going to specifically use metal cations because We can kind of get them dissolved in solution a little bit easier, and it's easier to test them in the flame that way. Okay, so we're going to look at a number of different metal cations and see what kind of colors they release when we put them in the flame. The color of light can tell us something about how far the electrons are going through the electron cloud. A bigger jump means that requires more energy, which means we're going to end up releasing more energy when our electron goes from the excited state to the ground state, when it de-excites back to its normal place in the electron cloud. A bigger jump that requires more energy is going to release more energy, which shows up farther down the rainbow in terms of visible light, like closer to blue or violet rather than red or orange, which would be like a lower energy jump. So we'll take a couple drops of each chemical, put it on the end of a Q-tip, run up and down through the flame, and see what color lights get released. First metal cation we're going to test is sodium. So it's on the end of this Q-tip. It's the Na plus ion that's dissolved in here and dropped onto the end of the Q-tip. As we run it up and down through the side of the flame, you get this bright orange color. Now the Q-tip itself will burn orange, but this is one case where this orange color is actually coming from the sodium. Right, so this is probably the least exciting one. Next up is potassium, so K+. So we get a little bit maybe of that orange, but we also get kind of a pinkish purplish color, which is really beautiful. And a little bit hard to see on the camera, but maybe pick it out a little bit. Next up is lithium, Li+. Ooh, we get this really neat, really deep red color from this one. Like a saturated dark red. This is calcium, Ca2+, so it's lost 2 valence electrons. Okay, we get a little bit of the orange, but also a little bit of red in here. So we kind of get like a reddish orange color from calcium. Next up is strontium. This is Sr2+. Oh, this is kind of a brighter, more vibrant red compared to the lithium, which was kind of a darker, kind of subtler red. This is like an in-your-face kind of red, kind of lighter. Here's barium, Ba2+. This one might take a while to get going, but once it goes, this is one of my favorites. Yeah, we get that kind of yellow color. It's like a golden flame. That's neat. Finally, we have copper. It's Cu2+. Let's get this in here. The liquid itself is kind of a bluish color, but when it gets put in the flame, it gets going. Yeah, it emits green light. It's a pretty vibrant green, too. So how can this be useful to us? Well, I've got an unknown chemical here, and it's one of the 7 that I've been dealing with, but I don't know what it is. It wasn't labeled except for saying unknown B. So this is unknown B right here. Okay? Now, if I run it up and down through the flame, it should give off a characteristic color of light from that flame as the electrons excite and then de-excite. From the excited state back to the ground state, they release light. Based on that color, I might be able to figure out which of those 7 it is. So we got a pretty strong red color there. And you might go back through the video and try and compare it to some of the others, what you see, and see what matches best. I'm starting to burn the Q-tip, so get a little bit more on here. Give it a couple more runs. Here we go. Very nice.